For any civilization passing on the dark side of the Earth, it's obvious that something very significant has happened here over the past couple of centuries, because the night sky is now ablaze with the lights of hundreds of cities across this planet, with a population of more than 1 million. And it would be very evident to that passing civilization that human technology and its ability to influence the planet has changed very, very dramatically over the past couple of centuries. And what I'd like to show you in this talk is just what your and my impact is on this wonderful planet on which we live. It really is a wonderful planet. This is an image taken by the NASA probe Voyager 1 as it was leaving our solar system on the 14th of February 1990. It's an image of our planet taken from 6 billion kilometers away. This particular image was suggested to be taken by the very famous astronomer and physicist Carl Sagan. And you can see just how small we are, how we drift in space as a cosmic oasis. And as Carl Sagan said, this is such a wonderful planet to live on. It's also the place where we make our stand. There is nowhere nearby that we can escape to, and there is certainly nowhere nearby which is anywhere near as wonderful a place to live as planet Earth. Venus is a Hadean world. It's certainly not the kind of place that we could set up colonies and civilization in the very near future. Its surface temperature is over 450 degrees Celsius. And this is an image taken of the surface of Venus by the Soviet Union's Venera 13 spaceship that landed here. And this particular image was taken on March 1st, 1982. This is not a place that we can easily live. There have been recent reports of the possibility of life high in the atmosphere of Venus, but certainly not a good place for humans to live on the surface. And our other nearby neighbour, Mars, often touted as a place that we might move to in the not too distant future, is also a desert. There's almost no water at the surface. There's a little bit below the surface and in the polar regions. The surface temperature is very cold. This would be like leaving the most magnificent, wonderful, verdant place you could possibly find to go and live in a planet which is effectively a desert. So again, not really a good place that we can escape to in the very near future. Back on Earth, as we've noted, something very fundamental is happening, and humans have now become agents of geological change. We move more Earth than all of the Earth's rivers. It's an incredible figure when you think about it. 316 gigatons of sediment, or 150 cubic kilometers, is produced by humans each year. And you can see the figures for rivers there. It's much smaller. So we're talking about an order of magnitude difference. We also use an incredible amount of water, something like 10,700 cubic kilometers of fresh water every year, or the equivalent of draining one Loch Ness every 6 hours. That's an incredible figure for one species' water utilization. Our energy consumption is absolutely vast. Something of the order of about 900 exajoules a year if you take all of the primary energy resources we use and also all of the energy that we extract from the biosphere. Now that to me is a figure which is just too vast. I can't really comprehend it. But you can think of it in this way. If you took an old style 60-watt light bulb burning through 60 joules of energy a second, well, basically that light bulb has to stay ablaze for about 450 billion years just to burn through a single year of human energy. And to put that in perspective, the universe is only a little under 14 billion years old. So basically your light bulb burns almost till the end of time. We also, as a species, change the atmosphere. We put about 37 billion tons of carbon dioxide into the atmosphere in 2019. And again, that's an order of magnitude greater than all of the Earth's volcanoes. Humans are also fundamentally changing life. Recent reports have suggested that as many as 1 million species may be at risk of extinction, and indeed, humans may be precipitating the 6th mass extinction event in Earth's history. And that would be terrible, because that would mean we would lose something like 75% of all of the species before many of them have even been recognized. So what I'd like to do in this talk with you is to ask the question, how did we get here? How did we become such a dominant element at the surface of the Earth? How have we changed things? Can we actually quantify the degree of impact that we've had as a species? And how must you and I change the way that we live in order for humans and also the rest of life on planet Earth to survive? These are fundamental questions that we need to answer in the very near future, and Earth scientists, of course, are right at the core of trying to find solutions to many of these questions. Let's begin then with, how did we get here as a species? It's a long journey, of course. It's a long journey which has left a really good fossil record. So, for example, our ancestors nearly 4 million years ago were walking upright. We know that because we can find traces of their footprints here preserved in volcanic ash at Laetoli in Tanzania. And these footprints are not of humans, they're probably of Australopithecines, a very, very close relative to us from which our own group of species may have arisen. But this means that we were walking upright nearly 4 million years ago. And of course, that upright stance may have been really important in terms of freeing our hands to interact much more closely with our eyes and ultimately with our brains. Around about this time, certainly as long ago as 3.3 million years ago, we start to make tools, or our immediate ancestors, the Australopithecines, begin to make tools. And this, of course, is the beginning of technology, a technology which would eventually come to dominate the entire planet. A little after that, as long ago as 2.8 million years ago, we begin to leave our fossils in rocks. And this time, you're looking at the jaw of an ancient human, because this is a human that belongs to our group, to the genus Homo. It's not a Homo sapien, it's not the same species as you and I, but it's one of our ancestors that lived nearly 3 million years ago in Africa. We have to jump forward again in time to around about 300,000 years ago, to a fossil locality in Morocco, where we can find the earliest evidence of anatomically modern humans, of humans that looked like you and I, that belonged to our species, Homo sapiens sapiens. As we come forward in time, we find increasing evidence of humans, of modern humans' ability to understand or to try and interpret the world around them. We start to find patterns etched into rocks from about 70,000 years ago, into little pieces of ochre, for example, in the Blombos cave in South Africa. And sometime after that, we also start to find widespread cave art from Europe to Indonesia, depicting many of the animals that we lived with in the landscape, and perhaps trying to understand how those animals thought so that we could perhaps hunt them in a more successful way. And indeed, we find evidence also that humans were hunting animals more successfully. They developed very, very sophisticated stone tool technologies at this point, and as humans expanded into new lands, they seem to have been influential in causing extinctions of large animals. For example, in the Americas, a little bit after humans arrived there, giant ground sloths disappear around about 10,000 years ago. Some of them continued on in the islands of the Caribbean till about 4,000 years ago, to eventually again met their demise as humans expanded into these areas also. We begin to develop agriculture as long ago as 10,000 years ago in many different places, from the Near East to Mesoamerica and to the Far East. And of course this allowed us to fundamentally alter the ecologies around us, a process that has been accelerating all the way through to the 21st century. And as a result, ultimately, we've engineered the means to feed billions of us by a process of selecting for particular plants, crops that could be very high productivity, and also in the 20th century through the development of the Haber-Bosch process for fixing atmospheric nitrogen to make fertilizers, which is reckoned by itself to be feeding around about 50% of the human population. Which means that at present, in 2020, there are a little over 7.8 billion humans on planet Earth. And this figure is rising by about 80 million each year, so by the population of Germany each year. Now that's a staggering figure. I find it very difficult to comprehend what 7.8 billion people would actually look like. So let's try and break this down into smaller packages. We could think of, first of all, about humans as potential fossils. So if you take the average weight of a human at about 60 kilograms, the average current weight of humanity is about 470 million tons. And even if you just take the skeletons alone, it's about 75 million tons. So clearly, straight away, good chance that we will leave a fossil record by the sheer numbers of us walking across this planet. Let's break that down a little bit further. Let's consider one large city, a megacity, for example. The metropolitan area of London, so the greater area, has about 13.9 million people. Now that too is a staggering number. I find it very difficult to comprehend London, and I think if you're standing in the centre of London, you can't really see the edge of it. You can't really grasp what 13.9 million people really looks like. Let's come down a little bit more. Let's take a medium-sized city like Leicester. About 330,000 people live in Leicester. And there are certainly places that you can stand in the city and you can look out to the edge and see the countryside around it. So you can begin to get a feel for what 330,000 people might feel like. Can come down a little bit further, down to a medium-sized town in the English Midlands, the town of Kettering, for example. It's got a little over 67,000 people. Again, when you're standing in Kettering, you can look out to the surrounding countryside and you can see the edge of the town. So you can get a sense of what 67,000 people looks like. Now let's compare that to the total wild populations of some of our close relatives. Let's see how many towns and cities they might make. The next two most populous primate species, this group of species that we belong to, after us are the Bornean gibbon, so Müller's Bornean gibbon. That's about estimated to be up to 375,000. So that's the total population of the next most populous primate species after humans makes one medium-sized human city, the city of Leicester. Let's come down the list a bit more to the chimpanzee. The iconic species, a very close relative. Well, there are perhaps between 200,000 to 300,000 of them in the wild. So that's the city of Derby, one medium-sized human city. Let's come down the list a bit more to the beautiful Bornean orangutan. Well, maybe there are 50,000 of these left in the remaining wilderness of Borneo, and that's not such a large remaining wilderness now. So the entire wild population is equivalent to one medium-sized human town, the town of Kettering, for example. Let's come down a bit more. What about the beautiful Sumatran orangutan? About 14,000 of these in the wild, so a little bit more maybe than the village of Kibworth to the south of the city of Leicester. And the beautiful and mournful golden lion tamarin looking out at you from this slide, about 1,000 of them in the wild, about as many as live in the human village of Thurkeston just to the north of Leicester. One small human village. And the point of this is to show you that you, as a species, and your fellow humans are 99.99% of the numerical abundance of all primates on this planet. We are completely dominant as a species relative to all of our brother and sister species. Let's go then to our next question. We've looked at how we've arrived here at our state of dominance. How have we changed things? Can we quantify the degree of change relative to some of the enormous changes that have happened in the deep geological past? Well, there are 4 ways in which we have very, very fundamentally changed the planet. And here I'm going to focus very much on looking at our impacts on life, because as a paleontologist, that's my speciality. Let's ask the question, how are humans changing life, and how is this fundamentally different from any previous change to life over 4 billion years of Earth evolution? Well, we're certainly causing extinctions. We've already talked about this. And these are some very evocative recent extinctions. There, top left, is the dodo, which of course went extinct on Mauritius only a few decades after it was first sighted. The beautiful Caribbean monk seal, there top right, went extinct, or certainly the last time it was seen was in 1952. The beautiful Yangtze dolphin, there bottom left, last seen in 2002. And there bottom right is the smallpox virus, which humans exterminated in the natural world in December 1979. All of these extinctions are evocative. They're something that we can relate to, I think, as a species, and all caused by humans. But extinction, though it is terrible, and though it is something that we are causing now on a wide scale to life on planet Earth, is not unique. It has happened many times before, and it happens as part of the normal processes of the cycle of history on this planet. What I want to suggest to you is that our changes to the planet, although they include extinction, are even more fundamental than this, and more fundamental than any change to life, perhaps for several 100 million years. So let's have a look at those changes. The first one we look at is the way in which we as a species consume energy. And here I'm going to focus on the way in which we utilize animals, for example, and show you that humans and their domesticated animals, cows and sheep, pigs, etc., represent more than 95% of all land mammals, which means that all wild mammals are less than 5%. Again, that's a staggering figure for one species, and the animals that species consumes to now dominate 95% of all the mammals on land. And even more so, we dominate the seas. We are unique for a terrestrial species in not just dominating the land, but also dominating the sea. You can see here a figure from 2016 that says that total world fisheries were around 171 million tons that year, of which we wasted about a quarter when those fish were landed. A terrible figure really, and a terrible indictment of our impact on the oceans. So that's just one very significant change. We've got another 3 still to come. This is change number 2, relocated species. This is the way that you and I have taken species from one part of the world and relocated them to other parts of the world. Sometimes beneficially, but sometimes invasively, in a way that is very damaging to native ecologies. This is one such introduced plant that we've translocated around the world. This is maize, originating in Mesoamerica, where it was cultivated as long ago as 9,000 years before the present, and then gradually it's spread around the world, as you can see here in this figure. And indeed it's left a fossil record of this change, which you can find in a record of its pollen recorded in lakes across the world as it was introduced. Even geographically remote areas of the planet have been invaded as a result of human activities. And this is something which is really unique, because even places like the Hawaiian Islands have had a whole range of plants and animals introduced to them, none of which would have been able to get there because of the isolation within the Pacific Ocean. And you can see there, if you just look at the number of native species versus the number of invasive species for Hawaii, then there's a staggering number of invasive species. And this is a process which has been taking place over a long period of time. So the introduction of the Pacific rat, for example, brought in by Polynesian people, probably in the 13th century, and that has left a distinctive fossil record. And then in the 20th century, for example, we introduced the giant African snail. And then we introduced the cannibal snail. And of course, the impact on the local snail fauna was really dramatic. The local snail fauna went extinct. And now what you find are these snails, and you find their shells preserved in sediments. You can see the faunal turnover between the indigenous native snails and these newly arrived snails introduced by humans. Change 3 is the way in which we've modified whole landscapes, the way in which we've anthropogenically altered those landscapes. A city, for example, is a massively modified landscape and a massively modified ecosystem. And I want to show you a figure generated by an academic at the University of Maryland, Earl Ellis, which has plotted up the way in which these anthropogenically modified landscapes have changed over time. What you can see here is that Earl and his co-authors have divided landscapes into used, semi-natural and wild. And you can see that in 1700, a little over 300 years ago, some of the landscape was used, so urban areas, for example. Much was still semi-natural, and about 50% of the landscape was still wild. Now let's jump forward 300 years to 2000. What you see now is that 50% of the landscape is used, and another 25% is semi-natural, and only 25% is wilderness. And in fact, this process has accelerated, and more recent estimates suggest that there is an even greater degree or percentage of the land has been human influenced in this way, perhaps over 90%. So this is a fundamental restructuring of ecosystems and ecologies on the planet. And of course, within those ecologies, there are strongly modified organisms, plants that we've manipulated, for example, to be more productive, that can feed more of us. But also we've manipulated animals. This is what we've done to chickens over the past 6 decades or so. We've increased their individual mass fourfold, and we've changed their life cycle so that now broiler chickens that are mass produced in their billions each year only live for a few weeks before they're actually packaged up and sent to us in plastic wrap for us to eat and to collect in supermarkets. A fundamental change. Change 4 is the technosphere. This is very much the idea of a gentleman called Peter Haff at Duke University in the USA. And this is the globally emergent system that includes humans, all of their technology, all of their associated social and technological networks, all of the things which bind us together and which support the 7.8 billion of us on this planet. And here you can just see this map showing the movement of materials like iron ore, oil, cement, coal, aluminium, etc., which is showing you the arterial networks of the technosphere. Now, the technosphere is a brilliant concept of Peter's, and it is a sphere. Like the other spheres of the Earth, the lithosphere, the atmosphere, the biosphere and the hydrosphere, the technosphere is global and it is everywhere. But it's only evolved in the past, few millennia, and it is overcoming the ability of the other spheres to meet its demands for raw materials. It hasn't co-evolved with them, and therefore it hasn't reached a stable state where it recycles the things it needs to survive over long time frames. Nevertheless, without the technosphere, most of humanity would not be able to exist. And Peter would say that technology, then the technosphere, like air, water, soil and food, has become a fundamental necessity for humanity to survive. And it's huge. If you just think about a factor like cement consumption, Between 1900 and the year 2000, the USA used about 4.5 gigatons to build its magnificent cities and skyscrapers. But in China, in 2016, they used half that amount in 1 year to build their skyscrapers, to build their gigantic and magnificent cities. And the physical technosphere is truly gigantic, about 30 trillion tons of physical technosphere. And you can see how that's subdivided into places like urban areas, trawled seafloor, plantations, railways, and roads. All of these areas that are strongly influenced by humans. Okay, we've seen at how we've arrived at this state of domination, and we've looked at how we can quantify the degree of change. We looked at 4 parameters, finishing with the technosphere, which is growing out of the biosphere. And we noted that we are using materials, the technosphere is using materials without recycling them, and that potentially can damage the Earth system and damage the Earth's life support systems. How then must we change quite quickly to survive? It's not just survival for us, but it's also survival for all life on this planet as well. Because we can argue very strongly that humans, in tandem with the technosphere, are gobbling up all of the Earth's resources. And of course, that's not a sustainable system in the long term. If human energy consumption continues to grow, then negative feedback mechanisms from our perspective will kick in. So, for example, ice sheets will melt as the climate warms, and indeed, we are beginning to see distinctive evidence of that both in the Antarctic and in the Arctic. And of course, if ice sheets were to melt, then that would have a major impact on global sea level. And we need to think that by the middle of the 21st century, 1.4 billion people will live in the low elevation zone near the sea, with countries like China, India, Bangladesh, Indonesia and Vietnam having the greatest population in this zone, and therefore susceptible to rapid sea level change. Think about those people, for example, who live on the world's great deltas. All of the world's great marine deltas will vanish by the end of the 21st century if sea level rises as fast as we're predicting. So think about the people who rely on the Ganges Delta, for example. There are over 100 million people that live here, and there are many tens of millions more people who rely on its agricultural produce. Where will they live? How will they produce food? This means that we, as a species, all of us, need a radical rethink of the way in which we interrelate with nature. And that relationship needs to be mutualistic. It means that we give back as much as we take, not the current parasitic system that we have, whereby we are simply taking and not giving anything back. Now, we can't return to a hunter-gatherer lifestyle, although that's a very sustainable lifestyle, as many studies have shown. But it seems also that this kind of lifestyle that all of us led through our ancestors suggests it can only support about 10 million of us living this way off the landscape. So therefore it's not possible for 7.8 billion of us to do that. And we also know that many past urban civilizations have failed because they've outlived the available resources in their immediate neighborhood. The demise of the Mayan lowland civilization around about a millennium ago, for example, seems to be linked to overuse of resources. The Mayan civilization, of course, didn't collapse at this time. The lowland civilization did, but Mayan cities lived on until the 17th century. They only really collapsed under the brutal regimes of colonialism. It's what finally expunged them from the landscape. And we also know that some past civilizations, or some past very sophisticated urban civilizations, have been remarkably good at sustainability. So Tokugawa Japan, for example, between the 17th and the 19th century, when the country was effectively closed off from the rest of the world, was brilliant in developing virtuous circles where materials were used in a sustainable way, because those materials were very limited in terms of their accessibility. And this led, for example, to whole groups of artisans developing who would be involved in recycling goods, mending pots and pans and ceramics, for example, recycling clothes, all of the kinds of things that we need to think about now in the 21st century, and giving us a good precedent also for the way in which Japan managed its landscape during this time, not taking too much from nature and being careful to give something back also. We can also learn from indigenous cultures like the Martu people in the Western Australian desert that are really good at engineering the landscape's diversity. They're good at doing this because it's also beneficial to them, because it means then they can harvest more lizards from that landscape which they enjoy eating. And they do this, for example, by burning back some of the vegetation in a very careful way, and that actually allows a greater range of plant diversity to develop, which supports a diverse landscape of animals also. It's of course in marked contrast to what Europeans did when they arrived in Australia. They introduced rabbits, of course, and those rabbits have decimated many areas, many ecologies in Australia, such that the rabbit-proof fence is now built across the country to prevent rabbits extending even further. It's a marked contrast with what the Martu people do in their landscape. We also need to fundamentally change our relationship with food. These are broiler chickens. We eat 63 billion of these birds every year, and there are something like around about 21 billion of them alive at any point in time, which is an order of magnitude greater than any wild bird species on the planet. And it can't be a fair way to exist, the way in which we produce these birds. They live for something like around 6 or 7 weeks before they're actually then packaged up for us to eat. We need to change our relationship with food in the way in which we consume also. So, even to make a burger with 2 meat patties in of about 100 grams takes about 170 square meters of land. And because of our voracious appetite for meat, that means that many areas of the landscape are being converted to pasture. Often, as a result of that, areas of the landscape are being deforested. And this too cannot be sustainable over a long time frame. Otherwise, we will not be able to live with nature. We need to leave space for nature. We need to follow the advice of the very famous American biologist E.O. Wilson, who has suggested that we need to leave half of the earth for nature. We really need to do that. Rewilding means that we do just that we give a space for nature, both within our cities, both within our agriculture, and also making truly wild spaces where humans don't impinge. Because if we don't start to make these changes, there are really 3 possible trajectories, I think, for where we can go. And 2 of those trajectories are not very good, both for nature and for us. The first of these trajectories is that human changes to life become short-lived and unsustainable and are marked with a mass extinction. That's where we're going in the not very distant future if we continue with the business as usual scenario. Another scenario might be that the technosphere evolves to become self-sufficient. It's getting more and more complicated. It's becoming more and more intelligent. Perhaps it might subsume or even supplant the biosphere. And there, of course, we're in the realms of science fiction. However, this is very unlikely. And it's very unlikely because the technosphere is appallingly bad at recycling the things it needs to survive over long time frames. And therefore, it is likely eventually to collapse. And with it, of course, would collapse much of the human population. Now, this is where you come in as the Earth scientists and the environmental scientists of the near future, because this is where you can make a major difference. You can help to evolve the systems that will foster a mutualism between the biosphere and the technosphere. And that will allow us to evolve towards a sustainable state where the technosphere can interact with the other components of the Earth system just as those other Earth system components interact over very long time frames. That's where we must evolve to in a very short space of time. It really needs the input of environmental scientists and earth scientists to help with this. But even then, I have to say to you that if we're able to do that, and if that new system persists over long geological timescales, you and I, as a species, will still have fundamentally changed the Earth system. And our changes are as profound as any of the changes to the biosphere over more than 4 billion years of biological evolution on this planet.